Hi guys, my name is Tensor. Today we're going to be building a neural network that will allow us to generate various forms of art by declaring different inputs and outputs in Clojure. We're going to be using the Quill library, which allows us to create animation inside of Clojure and Clojure script. We're going to use it mainly just to paint a few pictures. And these pictures will be painted based on the inputs and outputs that we put into our neural network. Each network takes a pixel location on the screen as an input, and then it will output a color. All the inputs and outputs get normalized, and they are normalized between 0 and 1. And then the networks are trained using what's called a hill climb algorithm. Let's get started here. We'll create our project using Lineagen. So we call line new quill and the name of our project, in this case Gen Art. This generates our new project, and we can cd into our Gen Art folder and type in cat project.clj, and you can see this is the generated project CLJ file. It's got our dependency for Clojure and the dependency for Quill inside of it. I'm going to use Emacs for this particular project, but you can use any text editor you like. Inside of our project.clj, we just want to make a few modifications. Mainly, we want to point the main map towards our genart.core namespace, and then we want to have ahead of time compilation, so we put in AOT and then we put in all. If you jump into your core file that was generated by the Lineagen template, you can see that there is a basic Quill application already created here. We don't need any of this boilerplate aside from the import for quill.core. We do want to create some mathematical helper functions, and so we'll create a module called math.clj. Here are the first two functions that we want to create inside of our math helper library. Both of these functions allow us to manipulate vectors. The first one allows us to multiply vectors, and the second one allows us to subtract vectors. You can see that we're making use of polymorphism here. If we insert a vector with one element, then it will just return that element. If we reinsert a vector with two elements, then we will map the operator of the respective function onto those two elements. For the multiplication function, we'll multiply a times b, and for the subtraction function, we'll subtract a from b. If we have more than two elements, then we want to call reduce, and then recursively call the function on a and b, and then on the rest of our vector. So this will essentially just iterate through our entire vector, multiply everything together, and give us the product. Now we want to create two more functions. One is for the dot product. We input two vectors, and then we want to call our vector multiplication on the two vectors, and then we want to reduce everything by adding together the result of this. So for those of you who know how linear algebra works, we take all of the vectors out of a matrix, we multiply all the elements inside of each vector, and then we add each of the products together to get our dot product. We also want to create a matrix multiplication function. This will take in m and v, and then we'll use the map function to map this Clojure, which calls our dot function, on v and m. We need a function to normalize our data to give us positive numbers, and so we create an absolute value function. This takes in a number, and if that number is negative, then we just invert the sign, so we make it positive. Otherwise, we just return the number back. Now, because our neural network is using random elements, we need to create a function to create random vectors and a function to create random matrices. The random vector function goes through and it creates a random vector of size n. It checks to see if rand, which is a random number, is less than 0.5, and if it is, then we return rand. If it isn't, then we return negative rand. And then we repeat this n times so that we get an n size vector. Then for our random matrix, we pass in n and m, n being the number of columns in our matrix, and m being the number of rows in our matrix. So what we do is we call random vector on m, and then we do this n times. And this will give us a random matrix of n by m size. Now we want to create the two transfer functions for our neural network. The first one is the sigmoid function, and you can see the actual mathematical function that we're creating here. It's just 1 over 1 plus e to the negative x. We take x, we multiply it by 5, then we make it negative, take e and raise it to that number, and then we're going to add 1 to that number, and then we're going to take 1 and divide it by the result of this. Then for the tangent hyperbolic function, we define it in terms of the sigmoid function. We take 2, we multiply by x, and then we also multiply 2 by the sigmoid, and then we multiply those two together, and then we subtract all of this by 1. Essentially, the tangent hyperbolic function is similar to the sigmoid function, except it was moved so that it gives us numbers between -1 and 1 rather than numbers between 0 and 1. And this will have various advantages inside of our neural network. Alright, so that's it for our mathematical library. Now let's create our network library. So we just create a file called network.clj. Inside of network, we want to require our math library, and we'll get all the functions. We'll just alias them so that we can call them directly. So first we'll create a record. Now a record is just essentially a shape of our data, and we're going to be using this as each of the layers inside of our neural network. So each layer will have a matrix, transfer or bias function, which will either be the sigmoid or the tangent hyperbolic function, and it will have a Boolean value that will say whether or not it is biased enabled. So this allows us to change the steepness of, say, the sigmoid or the tangent hyperbolic function based on what we're trying to do with our neural network. Now, because we're using a lot of random values in this, using the biases to create a bit of order can be good for us. We'll create a function that will allow us to create a layer. This will take in the number of inputs, the number of neurons, the transfer function, and the bias enabled Boolean. And we'll check to see if bias enabled is true. If it is, then we want to create a new layer record. This layer record we'll call rand matrix on neurons and inputs plus 1 if it is biased, and then we'll pass the function as our function and the biased enabled as our biased enabled. Now if our biased enabled is false, then we just want to call random matrix on neurons and inputs, and we want them to be just left alone. And then we're just going to pass back the function and the biased enabled value like we did before. Let's create our FeedForward function. This will take in our network and our inputs, and we'll use the loop construct, which will allow us to loop around in our function recursively. So loop lets us bind values. So we take net and we bind it to net, we take input, bind it to input, and then we want to bind 0 to I. If I is greater than or equal to the size of our network, then we want to just pass back input. Otherwise, we want to iterate through each of the layers of our network. So what we do is we use this nth function to get out one of the layers of our function based on the number of I. I is 0, we get out the 0th indexed layer of our network, and we put it in cur layer, and then we check if biased is enabled on that layer, and if it is, then we want to recur passing in our network, and we're going to map the function that we pull out of our layer, so our transfer function. Then we call our matrix multiplication on our matrix, which we pull out of our current layer. And we want to take our input, concatenate it with a list of -1, and then we want to increment I plus 1. Now, if our bias isn't enabled, then again, we're passing through the network. We want to map our function from our current layer, call our matrix multiplication on the matrix from the current layer, and pass back the input as it normally would be, and then we still want to increment I plus 1. So this loop will continue to happen until I is equal to or greater than the size of our network. While we're iterating through our layers, we also want to add an element of randomness to how our application is drawing everything. We create a function called mutate layer, and what this will do is it will allow us to create a new random matrix based on the inputs so that we can then change based on a random number. So we pass in the layer that we want to mutate and then the mutation chance, and then we want to check to see if a random number that we get is less than the mutation chance. If it is, then we let n equal a count size of our matrix, and then we let m equal the count size of our matrix on the 0th indexed. Remember that n is the amount of columns and m is the amount of rows. And then we want to set target equal to random integer n. So this is just a random integer based on our amount of columns. Then we'll create a new layer record, and we'll use a for loop to iterate from 0 all the way up to n. That's what this range n is. And we'll bind that to I. And we'll say if I equals the target, then we want to take and call our random vector on M. And this will give us a new vector for this particular layer. Otherwise, we want to call nth on the matrix inside of our layer input, and nth will get out the ith element of our layer input matrix, and then we'll get out the function and the bias enabled, and we'll pass back our layer input with the new stuff inside of it or without the new stuff inside of it. We'll make a simple abstraction on top of this mutate layer function called mutate. This will take in our network and then the mutation chance, and then we'll just map our mutate layer function to mutation chance and net, which is our network. Now we want to create a function called score. This will take in our network, our inputs, and our expected output. We'll bind output to a map calling FeedForward with our network and input in it. And then we'll take our expected output and our output, and we will call our vector subtraction on them. And then we want to flatten this out into one single vector. So if there are any repeated values, they'll get removed. Then we'll call absolute value on this, and then we want to add all the elements together, and we'll put this into result. And then we'll take that result, multiply it together, and pass it back inside of a list with it as the first element and network is the second element. And this will come in handy for when we print out stuff to the console so that we can see how our network is progressing. So now let's pull all this together and create our hill climb algorithm with all the pieces that we made. Hill climbing algorithms are optimization techniques that allow us to essentially take an arbitrary number and then incrementally change the solution to try and find a better fitting solution. We start with a random matrix and then we incrementally change it over time until we get better and better and better and better and better. At least that's the idea. Now, because we're just drawing pictures with this application, it's more or less just us trying to find the solutions that we're looking for and trying to get closer and closer to those values. So we pass in our network, our input, our expected output, and the number of iterations. And then we're going to call loop. We're going to bind net to net, input to input, expected output to expected output, our iterations to iterations, and then we're going to bind I to 0. Then we want to check to see if the number of iterations is equal to I. If it is, then we just pass back our network. Otherwise, we want to call mutate on our network and 0.33, and we want to repeatedly do this 500 times and bind this to gen. Then we want to take our score function, which is right here. We take our gen, we pass it in, we pass in our input for input, and our expected output for expected output. Then we call pmap, which is just map, but it uses parallelization. Then we want to sort this by the first elements, and then we want to get the first element, and we put it into our result. And remember, the first element will be a vector. So then we want to take that vector and get the first element out of it. Then we take I in iterations, and we divide I by iterations, and we turn it into a double, and we print it out. So we'll have a double on the left that'll be between 0 and 1, and then on the right we'll have the actual result that's moving up and down, and this will be a number that will also be between 0 and 1, but it will be a much more random number and something that is much bigger or smaller. Before we print everything out, we want to make sure that I mod 10 equals 0. So we'll only print this out every single time I is divisible by 10. If we don't print it out, then we want to recur on our second element from result. So we put this in for net. Then for our input, we put in our input. Our expected output goes into expected output. And then iterations goes in for iterations. And then we want to increment I by 1. Now that we're finished with our network logic and our math logic, let's move on to our core logic. We want to bring in Quill Core as Q, and we want to bring in GenArt Math and GenArt Network, and we want to be able to refer to these directly, so we just call refer to all. Then we create the constants for our application, so we want our window to be 500 by 500 pixels, and then our steps will be our incrementation steps. So we want to increment 200 times. We then want to create some normalization functions. These will allow us to take our inputs and normalize them based on y and x. So we call x multiplied by pi and then call cosine on it. And we do the same for y. We multiply by pi and call sign on it. Then we want to create our random network. So for this, I've created 4 layers. You can create more or less depending on what you want to do. Each layer has a number of inputs, then the number of neurons, then the transfer function that we want to use for this layer, and then the bias. For layer 1, we've got 4 inputs, 20 neurons, and we're using the tangent hyperbolic function, and we don't want this one to be biased. Then layer 2 and 3 will be 20, 20, tanh and true, and then layer 4 will be 10, 3, and the sigmoid function and true. Then we want to create a trained network, and for this one we just call our hill climb function on random network, and we also pass in inputs, outputs, and steps into the hill climb function. Now, speaking of inputs and outputs, we need to create those. So I'm going to use the exclusive OR pattern. So our inputs will be 1, 1, 0, 0, and then 1, 0, 1, 0. And then we want to normalize them for x and for y. So we pass in 1, 1, 0, 0, and 1, 0, 1, 0 into xfn and yfn, respectively. And then the outputs for the exclusive OR are 0, 0, 0, 1, 1, 1, 1, 1, 1, and 0, 0, 0. Now, this may seem a little strange to you guys why we're using a logical operator for this. Essentially what we're doing is we're defining our inputs and we're sending them into our neural network. So our inputs are 1, 1, 0, 0 and 1, 0, 1, 0. Then we have our outputs, which are expected outputs. So these are the outputs that we are trying to expect the neural network to get, which is 0, 0, 0, 1, 1, 1, 1, 1, 1, and 0, 0, 0. And so what our network will do is it will try to get as close to these numbers as possible. And based on the amount of runs that it does, it should get further and further closer to these numbers. Now keep in mind, with the Quill library, the top left corner of our screen will be 0, 0, the top right corner will be 0, 1, the bottom left corner will be 1, 0, and the bottom right corner will be 1, 1. Okay, so now let's create our draw function. This takes in x, y, and our network. And we take x and we divide it by our x resolution, which is 500. We do the same for y, and we set these equal to x norm and y norm respectively. And then we want to call FeedForward on our network with x norm and y norm, as well as calling our x function on x norm and our y function on y norm. We want to destruct the result of this into r, g, and b. And then we want to take r, g, and b and multiply each of them by 255 so that we can then rescale them as colors. We're inputting areas of our screen and then we're outputting colors. Interestingly enough, the more neurons that we put into this application, or into our network rather, the sharper things will be, the more chaotic they'll be, and the more interesting the images will be. Also keep in mind though that it will be more expensive to add more and more neurons to our application. Okay, so now let's set up the rest of this. So we need to create a setup function, and this will give us a background which will be white. So we just assign q \background to 255, and then we want the stroke weight to be 2. Then we want to create a draw function. We take our trained network, we assign it to network, and then we want to do a sequence. We assign x to the range from 0 to 500 and y to the range of 0 to 500. And then we want to call our draw function with x, y, and net in it. And we want to destruct the result into r, g, and b. And then we're going to actually draw by calling stroke float with r, g, and b, and then point with x and y. So this will draw all around our picture based on the inputs and the outputs. So the outputs are the colors and the inputs are the actual areas of the screen. And then we'll save each of the frames every single time we draw it as a PNG file. Then we need to kind of hook everything together. So we say def sketch leaf, we say the host is host, we want the size of the window to be our res x by res y. We key in our setup function and our draw function, and then we need our main function, which takes in our arguments but outputs nothing and does nothing. And here we go. If we jump into our terminal and we run line run, you'll see that a box pops up, and this is the box for our applet, and you can see that our console actually prints out the different steps, and then once it hits 1 it will render out the picture. So I'm going to add an extra layer here, and I'm going to make these 20 instead of 10. So if we run line run again, this will start the program. And you can see that it iterates considerably slower this time because it has to go through more neurons. Also, the actual rendering of the image will take a little bit longer as well. You can also fiddle around with the inputs. So say I just want to change this one to 1 instead of 0 and save it. And I'll make these inputs a little bit larger, so these will be 20 as well. You can see here that the image that was generated is a bit more complicated and interesting than the last few. If you enjoyed this tutorial, feel free to subscribe and like. If you have any questions or comments, feel free to leave them in the box below. And if you disliked the tutorial, then by all means downvote it as much as you like. Have a good day.